Hello and welcome to this week's discussion. Uh, in this week's discussion, we will be going through the basic control technique that is used to analyze linear system, and that is state variable analysis. So, what do we mean by state variables? So, state variables are those variables, the information of which at time t greater than less than 0 will give the information about any information about the system at any time t greater than 0. In other words, state variables, these are variables, better I should say, uh, the minimum number of variables of system. Information about which at t less than equals to 0 provides the knowledge of dynamics of the system for t greater than 0. The state variables are the minimum number of variables of a system. Information about which at t greater than equals to 0 provides a full knowledge of the dynamics of the system for t greater than 0. So that are state variables. Now, how do we achieve state variables? To find out the state variables, the most common way of that approach is to obtain the characteristic equation of the system. The characteristic equation plays a very important role in the analysis of linear systems. Why is that so? Because characteristic equation provides the poles of the system, which is unique for a given system. It provides the poles of the system. So whatever variables whatever transfer functions you may consider, but if it's of the same system, the characteristic equation or the poles of the system will never change. The characteristic equation is totally dependent on the poles of the system. Now let us consider a linear time invariant system described by the differential equation this. So where n is greater than m. So by defining the operator s to the power k equals to d to the power k by dt to the power k is from 1 to n, we can write it in S domain as follows. Now the characteristic equation becomes basically the denominator of the transfer function. So characteristic equation is the denominator of transfer function which is equated to 0. Else it is just an expression. So when we equate it to a 0, it becomes a equation, characteristic equation. So this equation gives me the poles of the system. So again, if we have this differential equation format, we will get a transfer function format. The characteristic equation will give me the poles. Now, the state space equations are represented in terms of two equations. The first equation is known as the state equation, which is represented as x dot equals to ax plus bu y equals to cx plus du. This above equation is known as the state equation. Why is it called state equation? Because it defines the dynamics of the state with respect to the input. So dynamics of state x dot is a linear function of the states itself and a linear function of the input. So this is the state equation, and the next equation is the output equation, where output y is the linear function of the states and the linear function of linear uh, related to the input. So this is known as output equation. So this is the backbone of state space analysis. So from these expressions, how do we obtain the transfer function? Let's see. So from characteristic equations, how do we obtain the state equations? How do we obtain the transfer function? As I have said, x dot equals to ax plus bu. So and y equals to cx plus bu. Now taking Laplace transform, we can write as s times xs minus x0 equals to 8 into xs us. Okay, so now simplifying the terms, we can write. Okay, so since we are considering transfer functions, as we know that transfer function, the initial conditions are completely relaxed to obtain a transfer function. So to relax the initial condition, this term becomes 0. So now simplifying the terms, we can say xs s into identity matrix minus a inverse b. Now taking the Laplace transform of the output equation, we can write ys equals c xs plus d us. So now putting this here, we can write c is identity minus a inverse b plus d S. Hence, output lap Laplace transform of the output and the Laplace transform of the input ys by us is equals C si minus A inverse B plus D. So this is the expression that is being written here. So this has arrived in such manner, and this inverse can be again written in terms of matrix expression as adjoint of si minus A by the determinant of si minus A. So the as I said, the so the denominator here is si minus A. So the roots of this equation is the poles. So from here we can know whether the poles are real or complex conjugate, etc. So if we equate it to 0, we obtain the characteristic equation of the system. Next we come to eigenvalues. So the roots of this characteristic equation are also known as eigenvalues of the matrix A. So this is matrix A. So the eigenvalues of this matrix A is also equal to the poles of the system. So what are basically eigenvalues? So eigenvalues are those values for which uh, the vector transformation, the vector achieves a maximum value. So uh, in simple terms, eigenvalues can be represented as eigen is obtained from lambda I minus a so A times some vector v is equals to lambda times that vector. So if we are multiplying a vector with the matrix, we are doing a kind of a linear transformation, as in, so the matrix A has all linear all constant coefficients. So when you are multiplying the vector v with A, we are basically doing a linear transformation. We will obtain, if A is, let's say, n cross n matrix and V is n cross 1, so AV will again give me a n cross 1. So it's basically a mapping in the same n cross 1 space. So what eigenvalue states is that, so since it's a mapping in the same space, eigenvalue states that the resultant vector is nothing but a linear uh, not linear, I should say, constant multiplied with that same vector. Since it's a linear transformation, constant multiplied with the same vector, and this is known as the eigenvalue. So if the coefficients of A are all real, the eigenvalues will be either real or complex conjugates. That's for sure because the coefficients are all real. One complex term cannot be there, hence the coefficients would have been complex. Other thing is that summation of all eigenvalues is equals to the trace of A. What do you mean by trace of A? So if we have is the A matrix n cross n, and if this is the diagonal elements, the summation of diagonal elements is the trace of the matrix. So if A is non-singular with eigenvalues lambda I 1 to n, for A inverse it will be 1 by lambda the eigenvalues, and the eigenvalues of A and A transpose are the same. Okay. So some important things to consider, that if the eigenvalues are on the left hand side, that means the poles are on the left hand side of the S-plane. If eigenvalues are on the left hand side of the S-plane, poles are left hand side of the S-plane, and hence the system will be stable. If it's on the right hand side, the poles are also on the right hand side, and hence the system won't be stable. So yeah, so eigenvector are those vectors for which that linear expansion occurs. That is, as we said, if it's a matrix A, vectors when it is multiplied with a vector V, we obtain a linear expansion of that vector V. So these vectors for which this equation satisfies is known as eigenvectors, and this linear expansion is known as eigenvalues. Eigenvectors are used to make linear transformation understandable. So eigenvalues provide where the response is maximum, while the eigenvectors provide the direction of maximum response. So basically, so when this linear this expression holds good, the eigenvalues that we obtain, this lambda, it's basically the maximum response of the system, and these vectors provide a direction of the maximum response. So here, if we have an example, consider the following state variable. So this is a state variable. So A is 1 0 minus 1 minus 1, B is equals to 1 and 1. So what will be the eigenvalues? Mod of S I minus A, that is equals to S minus 1 1 0 S plus 1. So that is S square minus 1 equals to 0. So lambdas are either 1 or minus 1. Yeah, so 1 or minus 1 are the eigenvalues. Now we need to find the eigenvectors. So how to find eigenvectors? A v equals to lambda v. So I can write this to be A minus lambda I v equals 0. Not the other way around, lambda I minus A equals to 0. A is 1, 0, minus 1, minus 1, minus lambda. So first let's consider 1. 1 into I, the identity matrix 1 0 0 1. So this gives me 0 0 minus 1 minus 2. Let this be v11 v12 0 0. expression, it is minus of v12 equals to 0, minus 2 v12 equals to 0. So basically we know that v12 will be 0 and v11 can be any value. So it will be some multiple. So hence the eigenvector v1 is equals to 1, 0. So here it can be any linear combination of this. So 1 can be into some any constant k. So let's consider, we can say that it will be linear, the vector will be any linear, any multi-scaled version of this vector 1, 0. So this is my first eigenvector 1, 0. The second eigenvector is 1, 0, minus 1, minus 1. Minus, it will be minus 1, 0, 0, minus 2, minus 1, 0, 0. So considering v21, v22 is to 0, last statement gives me nothing. First is 2v21 minus v22 equals 0, which gives you v22 equals to twice v21. So we can say that it's a linear scaled version of the eigenvector is 1, any scaled version of this will 1, 2 and 1. This is how we need to find eigenvalues and eigenvector. Next we come to the concept of controllability. So a process is said to be controllable only when we can change the input variable in order to bring the states to their equilibrium condition. So the concept of controllability states that whether we can change input in such a way that the states return to their equilibrium position or values. So in case any state cannot be brought to equilibrium position by change of input, we consider it to be a uncontrollable state, and those states are changeable, or those can be returned to the equilibrium condition by changing input, are known as controllable states. So the process is said to be completely controllable if every state variable of this process can be controlled to reach a certain objective infinite times by some unconstrained control ut. So if any one of the state variables is dependent of the control ut, there would be no way of driving this particular state variable to a desired state infinite times by means of a control effort. So that's what we refer to as the uncontrollable state. the concept of controllability that is stated here is a state controllability. Similarly, we can define it also for the output, that we can change the output by changing the input. We say it to be output controllability, and if it cannot, it's an uncontrollable output. So to check the controllability of a system, we need to check the controllability matrix, which is represented this form: S equals to B AB A square B up till an minus 1b. So if the determinant is finite, we can say that all the states are controllable. If the determinant comes out to be 0, we have certain states that are uncontrollable. So if we have such a system, we can find out S equals to B. For this system, let's just do the math. So S is equals to B AB A square B. So from here we can state that B is 0 0 1, AB is 0 0 minus 1 0 3, and A square B is minus 1 minus 3, so it's minus 4, and is 0, and minus 1 9, so it's 8. This is the thing. Now if we consider finding its determinant, det of S, it is, these two are 0, so let's consider for 1. So if we consider it, it's always 0. So this S is singular, hence the system is not controllable. There are uncontrollable states. Next we come to observability of the linear systems. The system is completely observable when we state that every state variable of the system affects some of the outputs. So the state variables will affect some of the will outputs of the system. So similar to controllability uh, analysis, the observability is analyzed by considering this matrix, observability matrix, and finding its determinant. If its equals is finite, then we say all the states are observable, that is their effects are observed in the output. And if the determinant is equals 0, the some of the states are unobservable in the output. Thank you.